I love owls. Owls are, they're, yeah, Solvay's favorite bird. You gotta be careful with an owl, though. They are, they are predators. They eat stuff. Well, you're darn right I read the book. Who knows? Okay, let's go back to where we were and we'll zip through it and we'll get to the part that we need to get to. Remember that before we wanted to consider the limit of this function. And we said, what is the limit as x approaches 3 of 2x minus 1? And we said, well, it's obviously 5 because you can plug it in. Then we looked at a piecewise function, and when you plug in 3, you get a value of 4. So you can't simply plug it in. And what we did is we tried to get really, really, really close, okay? We tried to look at that portion. We tried to look at that portion to try to find a certain tolerance. In fact, we said, how close would you have to get to x equals 3 to ensure you're within 0.01? We did a ton of those problems yesterday, didn't we? And you guys found, how close you have to get an x value so that your y value has a certain tolerance to it. The question is, can you be sure that for all x values within that boundary that the outputs will remain within 0.01 of 5? And the answer is not really. The idea is your boundaries, okay? What if we were to, you guys saw examples yesterday, we went to 0.01 or 0.02. The question is, are you 100% sure that we could find a suitable boundary then for, say, 0.000001? Can we get infinitely small and be really sure about the behavior of that function? Well, true or false? You guys know the general behavior of a line. Yeah. And it doesn't do anything real funky, does it? But there's certain functions where we have to be very particular about the behavior, even when we get down really, really small. And so mathematics doesn't say, well, if we're within 0.1 of error, if we have a tolerance of, say, 0.1 for the limit, that's going to be good enough. If you estimated the limit to be 5.01 or 4.99, that's good enough to say it's 5. In mathematics, we say no. 0.1 or 0.01 is not close enough. We like a number like this. Number like 1 over infinity. Infinitely small. Something that is infinitely small is better for error. We like that. If you were to give an estimation, if you were to choose a number on the number line that best represents the number 1 over infinity, what would you call that number? Zero. 1 over infinity is basically 0, is it not? Here. Nearly the same. Thus, since we don't want to just come up with an estimation, we want to use what we call the formal definition of the limit, the precise definition of the limit. You will have to memorize this perfectly for your next test. Would you like to learn this on tomorrow? All right. So, I'll finish the parentheses. Thank you, Larry. So, now we're ready to learn. So, I will go ahead and do this, okay? I will teach you the song tomorrow. You are going to have to memorize this. This is part of your test. Why did I make you guys do this? I told you a story about Sam Stanley, right? The other reason is the test is too easy without this. So now it's a little bit more challenging. So let's draw it out. Let f be a function. Defined on an open interval except possibly at point A itself. There's a lot more. So, okay, so let's draw a function. Draw something like that. It's defined on a given interval, an open interval. So, meaning it has a domain to speak of. And then we're going to talk about this very important value, A. Let's say right here. Now what that means is except possibly at A, in order for the limit to exist at A, do I have to actually have a spot there at A? If I had a hole right here at A, would that be acceptable as well? Yeah, I could still have a limit, even though I got a little hole right there. That's okay. So I'm just going to, I'll have it filled and draw a hole so you could have either or, okay? Then we like to say that the limit as x approaches A of the function is equal to L. Is that notation you guys are familiar with? You sure are. And I'm going to draw that. That means that as the x values approach A, that the y values approach a number that we call L. We all good so far? I shouldn't have put a period here. We can say this, that this is true if we do what we did yesterday. And here's what we did yesterday, except we're going to put a few different letters in there. We're going to use the Greek alphabet. If for every number epsilon greater than 0, there is a number delta greater than 0. Sure, we'll do delta real quick. So, sorry. So capital delta is like that, but the small delta, I'll do my best here. That one's the best. This was probably my best one. Some people do it like this, and I think that's kind of lame. That's getting because the ancient Greeks didn't have capital letters. Duh. We don't want to dip into that. Well, I'm just saying that's what sometimes people represent as delta, but the Greeks didn't have capital letters. You know that. In fact, the Greeks in their writing, like if you read ancient manuscripts that are written in Greek, they don't have any punctuation and there's no space between the words either. So literally, if you look at a page that's written, there's like 100 letters by, say, 50 lines. And it just looks like a huge crossword puzzle. And just from the context of the grammar and everything, you have to understand exactly where things are pulled apart. So, we got little delta. This is the most important part, guys. Epsilon is your distance from the limit for the y value. So let's say I put this spot right here. This distance right here is what we call epsilon. So this is L plus epsilon. And again, this distance is epsilon, so this is L minus epsilon. So that's our tolerance of error. Remember that? So that's like what we did yesterday. We put those two spots up there, right? So epsilon is like our tolerance. And then those correspond to some x values, right? And so from there we drew down these x values. I know that these are not the same, so I apologize for the... But those are my delta values. So this is A minus delta. This is A plus delta. And that's the drawing you have to have imprinted in your mind. So that's why I wanted you to go through the work yesterday. Do you see why I had you do what you did yesterday? So now you see that. Now that's there. And so we've set the premise, okay, the limit as x approaches a of f of x equals L, that is true if for every number epsilon there is a number delta such that, this is the part you'll hate, I'm sorry, don't throw things at me, the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus a, which is less than delta. And that's it. Did somebody throw something at me? Who missed? Was it Larry? Was it Anna? So you should remember that epsilon is the distance from L, and delta is the distance from what? Yes. So you may wonder what these absolute value signs is. You may wonder what these absolute value signs are. They are used to represent distance. Distance. Okay, so if you choose any value of the function, say here, f of x, well, f of x minus the limit, whether you get positive or negative, the absolute value of it should be less than the epsilon value. So this is how we close in on one spot. We close in on one spot. Okay? So we have two tasks. Number one is to practice problems like we did yesterday, but understanding these parts to it. And then second of all, tomorrow we need to write a proof. Good times, good times. All right, so let's try an example. We'll do two examples, and then I'll give you your assignment. You're going to have some homework tonight. What's that? Yeah. Okay, consider the function f of x is 1 over 2x. Find an interval for x values such that the y values will always be within 0.2 of the limit as x approaches 2. So first of all, I'm going to write a limit. We only got the front page. Let me pause the video. So what is the limit as x approaches 2 of 1 over 2x? 1/4. So here's what I want you to realize. Okay, here's what we're doing. Okay, I'm first going to plot that. So if I go over to 1, 2. I have that value, which is a fourth, which is L, right? So what I'm trying to do is I'm trying to ensure that the limit is in fact 2. So I want to, see how close are the values to 2 around there. What x values would I plug in to get y values that are really, really close to 2? And so here's what we say. Distance from L, that's this expression. The absolute value of f of x minus L should be less than epsilon. And we also have this piece, the distance from my a value is that absolute value of x minus a is less than delta. Now, here's the important part. Let's see if you can identify the appropriate pieces to this. A for the day. What is f of x? One over 2x is f of x, right? What's L? 1/4. What is epsilon? Epsilon is 0.2. Epsilon is 0.2. Very good. Okay, so let's write that. Absolute value of 1 over 2x minus 1 over 4 should be less than 0.2. See where I got all those pieces? So I'm going to put this spot right there and this spot right here. So some of you guys were already trying to calculate these. If this is 1/4 or 0.25, what's going to be the top part? 0.45. It's going to be the bottom part. 0.05. All right, so that's kind of the epsilon piece. So now you can see that there's corresponding x values. That's where the delta comes in. Question. I added 0.2 to 1/4, and I subtracted 0.2 from 1/4. Okay, so everything has to fall within that boundary. All my outputs have to fall within that boundary. So now I have the absolute value of, now we'll do the distance from A. We have x minus, what's A? 2. So many people last year couldn't identify what A was. A is the number that you're approaching. It's probably because I often called it x, because it's an x value, but I will make sure we refer to it as A. So we have absolute value of x minus 2 is less than delta. So what we're doing in this process, everybody, is we know our epsilon. We're trying to find our delta. So this is the problem set up. I solve it the way we did yesterday. The reason why I'm having you use this notation is so that you understand it as we move forward. So let's give this a shot. I have to find delta. Can somebody give me an equation that I need to solve? .45. And 1 over 2x is equal to 0.05. Very good. We'll cross multiply and solve. 1 is equal to 2 times 0.45 is 0.9x. Divide both sides by 0.9. 1 divided by 0.9 is 1.11. I did what Solveig did. So this is 9/10. I flipped it, multiplied by reciprocal, so you had 10 over 9. 10 over 9 is 1.1. You know it too. All right, we cross multiply. 1 is equal to 2x times 0.05 is 0.1x. And I divide by 0.1. You know that 0.1 is 1 over 10. And so you get 10 is equal to x. So which is which? Which one is this one? 1.111. Right? What is this? Nope, graph is not to scale. Now, true or false? Those are my delta values. False. What would my first delta value be right there? 8. So, if you chose any x value within 8 units of 2, would you be guaranteed to come out within this range here? No. If you choose 8 units away, you could be way back here at -6 and be on completely the other side of the graph. True or false? If you choose a value within 0.89 of 2, does that guarantee? Yes, you have to choose a smaller output. If we move to 0.89 to either side, our outputs are going to be within that epsilon tolerance. And so the question was, find an interval for x values such that y values will always be within 0.2. You could set up the interval. You could say, your interval would be, say, 1.11 to 2.89. You could add the 0.89 on each side. If you simply write this delta equals 0.89, that'll be sufficient. The key to what we're going to do in the future is to identify the appropriate delta value. Choosing delta is extremely important. And so we choose simply a delta value equal to 0.89, and we are done. We've guaranteed it. Now, again, we had a tolerance of error, 0.2. Tomorrow we're going to go to 1 over infinity. Let's do one more example. Let's involve some trig. I know how much you guys like trig. I know your trig teacher from last year. He was pretty good, I've heard. So hopefully you remember everything you were supposed to remember about trig. Consider the function f of x equals 3 sine of 2x. Find an interval for x values such that the y values will always be within 0.1 of the limit as x goes to pi over 8. So let's look at the graph first. What does this graph look like? It's a wave. What is the amplitude? 3 in this case because of the 3. The period is, if you remember, 2 pi over b. So the period will be pi. So let's just mark out pi. We divide it into how many parts? 4. Does sine start at the middle or the min or max? Middle. Starts at the middle. It will top out right away. It will come back down. It will bottom out. It will go back up to pi. This is your graph of f of x equals 3 sine of 2x. Got it. If you can't get that from memory, go ahead and use your graphing calculator. But you have to be able to produce that. Okay, so now here's what I'm going to write. The limit as x approaches what? What are we approaching? Pi over 8 of the function. What's the function? Has to equal something. What is the limit? If I plug in pi over 8, what's 2 times pi over 8? Pi over 4. What's the sine of pi over 4? Somebody want to do it on your calculator? Well, it's the square root of 2 over 2. If you remember that. Probably not. That's all right. So multiply by 3, and you get 3 square roots of 2 over 2. So somebody on your calculator take 3 times the square root of 2, and then divide it by 2, and we'll get a numerical or a decimal answer. 2.12. 2.12. Got it. So, pi over 8. There you have your spot, right? Let's write the two parts of our definition for the limit. The absolute value of f of x. What's f of x? Minus L. Has to be less than epsilon. 0.1. How do we make that happen? We choose the appropriate delta. The delta means that x minus what is a? Pi over 8 has to be less than delta. So the missing part to this type of equation or this type of statement is that we do not have an appropriate delta value. In order to figure out the appropriate delta value, we need to set up a couple of equations. Let's first draw what we're talking about. If L is equal to 2.12 and our tolerance or our epsilon is 0.1, what is going to be our top value? 2.22, what's going to be our lower value? Yep, 2.02. So you can see, very difficult to draw, but that's what we have going on here. Can somebody give me one equation? 3 sine of 2x is equal to 2.22. Give me the other one. Got it? True or false? When I solve for x, I'll have my delta. False. You'll simply have your x value, and then you need to figure out your delta from that. See? Absolute value of x minus pi over 8, so we'll actually have to add or subtract a pi over 8. So let's finish off these two. Let me grab my calculator. Make sure you got your calculator out, and let's work in radians. What does the fox say? Miss Nelson hates that song. Come on. Come on, calculator. You can do it. There it goes. No. So, yeah, first of all, mode, make sure you're working in radians. Everybody in radians? Okay. Now, come on over to this graph, and what we have here is 3 sine of 2x is equal to 2.222. What should I do first? 2.22 divided by 3. Very good. You get 0.74. So, sine of 2x is equal to 0.74. How do you get rid of sine? Reverse sine. Sine inverse. You have to now retake trig. Sorry. Sorry, you can't say reverse. That's like the cardinal sin. Okay, so you sine inverse and you get 0.8331. So 2x is equal to 0.8331. How do I get rid of the 2? Divide by 2, and I get 0.4165. Let's review the process over here again. I have 2.02. What do I do first? 2.02, I divide by 3. Then I sine inverse the answer. I taught the pre-calculus class how to do the answer thing. They were like, that's the coolest thing I've ever seen. Oh, awkward. Second, and then the negative side, there's an answer there, so grab your previous answer right there. Okay. Yep, that's all right. And then once I have that, I divide by 2. And so I got 0.3694. So those are my decimals. And so we have this 0.3694, and we have this 0.4165. Are those my delta values? No. I have to figure out pi over 8 first. So pi divided by 8, and we get 0.3926. So which one's closer? We don't really know, do we? We need to find the difference between the two of them. So let's find the difference, which, as Megan just said, is the delta value. So I'll find the difference, and then I'll be able to identify exactly what our delta value should be. And so if we take that 0.392 value and we subtract 0.3694, I get 0.023. And if I grab my other value and I go 0.4165 and I subtract off of that 0.3926, I get 0.024. So what is my delta value? That's it. .4, page 100. Numbers 1 through 6. Now, you guys, they don't ask the questions exactly like I did the problems. You might have to, think through them just a little bit more. But try to do the ones that you can. Okay, no, here's what we need to do. We need to outline this so that you guys have something to go off of, okay? Just so I make sure that I get this straight. So you can write this down. Problems 1 and 2, here's what you want to do. Same as yesterday, same as worksheet. Problems 1 and 2 are the same as the worksheet. Three and 4, all the work is done from our notes for 3 and 4. Just do the final subtraction part. That's all you have to do. That's all they're looking for. All they're looking for is delta. All the work is set up for you in 3 and 4. All you got to do is find the delta. So it's supposed to be real straightforward and easy. Finally, 5 and 6, just like the notes. So if the language that they use in the book confuses you, that should give you an idea to run for. Please try to get as much as done as possible, because I would like to try to do a very basic proof tomorrow, okay? By the way, I'm meeting, so I won't be able to help you.